Hello everyone, we're going to look at Jovian planets in this video. You guys, but you've done good work what I've seen. So there's a lot of stuff going on here. Next video is going to be on small objects, asteroids, and comets, which are very similar to some of the stuff we're going to talk about here. And with me today are the greatest cats in the world, mine. They're asleep, they're passed out, so I'm trying to keep them calm and sleepy. So here's an overview of the planets. What we notice from this is that they're all fairly bigger than Earth. Uranus and Neptune are kind of comparable, but they're going to be like on the order of 10 times the size, or 14 or 17 times the mass. They're fairly, and they're also blue, which is kind of unusual. Is Jupiter and Saturn are orangish. None of them are, cratered rocks, so that's kind of interesting. The densities are fairly low. Saturn could float in water if you had enough. And what we see out of this is that everything is hydrogen and helium, but Uranus and Neptune also has ice and rock. That's what the hydrogen compounds are, is ice. So that's what we see is that hydrogen compounds here, water, methane, ammonia, that sort of stuff. Compounds with hydrogen that can form ice. And so there's a density difference here. It's Uranus and Neptune are a little bit denser because they have less hydrogen and helium. So it's not a real pattern here. They're fairly low density for being planets. And we're not altogether sure what the deal is with Jupiter. Should it be even lower density at this point? And what we're going to realize is that hydrogen and helium is compressible gases. And if you add mass, it's going to compress the gas more. So what happened with Jupiter is it got denser as you put more and more hydrogen and helium on it. It actually got to a point close to which it would start shrinking. It got near its maximum size. And so, Jupiter can grow a little bit more, but it's going to take lots of hydrogen and helium to make it grow. And then eventually it's at its max size. So there's some other stuff going on. No planet is perfectly spherical. The spherical shape would be caused by gravity alone, but there's also rotational effects. Basically, the center gets pushed outwards essentially by centrifugal. You have a combination of the material properties of the planet and gravity causing it to basically slip outwards and squish. And the Jovian planets are more, you would think, because they rotate very fast. All right, so layers. All these things are layered up in different ways. We'll look at Jupiter in particular. For the most part, there's no solid identify the solid surface. Is that you have a gas layer at the top, and the pressure increases, and the cores are going to be made of solid things like hydrogen compounds and metals and rocks. But you have these layers where, in Jupiter, you have liquid hydrogen forming, and then you have metallic hydrogen, which is very unusual. And we get to such high pressures and high densities that it becomes unclear if the material's solid or if it's soupy or what. But this is the kind of layer structure that we get. And for Jupiter special, we get metallic hydrogen because the pressure is so high. And it effectively acts like a metal. It acts like a conductor. Electrons normally stuck to the proton and the hydrogen are now free to move around. So core is going to be like one of the original planetesimals in the formation of the solar system. It's going to be something made out of rock, because Jupiter's past the frost line, it'll be made out of ice, of hydrogen compounds. And so the core is about the size of Earth in radius, but it's about 10 times as massive. That's your rule of thumb. Things that are about 10 Earth masses are big enough to start holding on to hydrogen. So the cores are pretty similar. They're going to be like the original planetesimals that can form, but you'll have different things going on. In Saturn, you'll have you'll have wider layers near the surface and shallower layers inside. Not nearly as much metallic hydrogen. And Uranus and Neptune aren't quite big enough. So you're going to have layers of gaseous hydrogen, and then layers of ices, of water, methane, ammonia, before you have a core. So Uranus and Neptune are a little different, and their makeup is going to explain why they look the way they do. So with all of this stuff, there's a lot of stuff here with potential energy. And Jupiter radiates more energy than it receives from the sun, about twice as much. And what's happening is that the original configuration of the planet stored a bunch of potential energy. And as the planet contracts, that potential energy turns into thermal energy and is radiated out. So it's the energy that's available is the energy that was there at formation as potential energy. It's going away in contraction. Saturn is about the same, and it's sort of the same method. Instead of contraction, we figure that Saturn has a fair amount of helium in the upper layers, and it is raining out. And so the helium itself is differentiating inwards, and that change in potential energy is generating the energy that's radiated away. Um, Neptune is a little more unclear. It certainly radiates more, but we think it's due to contraction, but we're not certain. Uranus doesn't seem to radiate that much at all. So, all right, so we can't really talk about geology because there's no surface. We kind of have to talk about atmospheres. We have to talk about weather. And what we're looking at here is the Great Red Spot on Jupiter, which is basically a massive hurricane that's been swirling. It's been there for about 300 years, at least, maybe 400 years by now. Atmospheres look very similar: tropospheres, stratospheres, thermospheres, exospheres. And where we would consider the ground layer is basically the cloud tops. And so basically at the end of the troposphere. So in the clouds, we have different compounds. And the compounds make different colors. Ammonia is going to be sort of a pale yellowish white, and ammonium sulfide is going to be this reddish color. And then water ice is going to be more watery ice white. So we have these different layers, and most of the planets have these different layers. Uranus and Neptune are special in that they have methane. And methane is going to give a completely different outlook. But the layers in the atmosphere are pretty similar. Saturn's colors are a bit more subdued because the cloud tops occur at lower altitudes. So you can see in this picture here, there is, red streaks across. That is the ammonium sulfide, and there's white bands going the other way. That is the water and ammonia. In particular, the ammonia layer is going to be the uppermost layer. And these bands, if you remember talking about the Earth's uh, weather patterns and climate patterns, there's north to south cells of wind, and the Coriolis forces three bands of circulation north and south. when inside those bands the winds go east and west. And so that's what's happening here. There's several stripes as the Coriolis force is directing stuff trying to move up and down in the atmosphere, move in stripes east and west. And you're going to have circulation between the bands. In some places, you'll have an upwelling of convective current, and it'll show one type of cloud. And in other places, it'll be a downwelling, and you'll have the other color cloud. And sometimes you'll have circulation. You'll have storms. Patterns, colors are pretty similar, but you notice they're a lot more subdued because they're further from, don't seem to have that striped appearance because they're dominated by the blue color that it results from methane gas. Is that methane that's going to absorb lots of red light and reflect blue light, so they look blue. Uranus, we can't really tell if there's any clouds here. It's basically a haze. Neptune, we can see a couple of dark spots and dark stripes and a few white lighter spots around it. Right, but the circulation, right, is explained here in more detail. In a particular band, you have those provide the ammonia clouds, and then where the gases are falling, you're seeing the ammonium sulfide. It causes the different, and at the edges is where you get shear, you get the winds blowing, and you'll get circulation there. And so you get something like the Great Red Spot is basically between two bands. It's formed a high pressure area that's persistent. It's existed for a long period of time. So all of these places have what we would call strong winds and storms. And they all have magnetospheres, which are massive. We talked about the Earth's a little bit. We talked about terrestrial planets and magnetic fields. Jovian planets have massive, massive magnetic fields. We can see Io in the inset picture. Io is orbiting and happens to be leaking dust all over. It forms a big donut, the Io torus. But magnetospheres tend to direct the solar wind away and toward the poles. So the Jovian planets are going to have aurora at the poles. You can see them, these circles in the at the polar regions of the planet. And so all the planets have very substantial magnetospheres. Jupiter's the biggest by far. And now, that's basically the planets. That's what we know about them. The moons, I think, are a fair bit more interesting. Here, what we have is the Galilean moons, and you can look at them and see that there's interesting stuff. Io, you can see spots that maybe look like craters, but there's not enough of them. And you might think, well, maybe those are volcanoes. You'd be right. Europa looks like ice that's been scratched up, like figure skaters have skated over it. And you're seeing lines in the patterns of the icy surface. Ganymede, you can see some features of ice, but you can also see some features of cratering. Callisto is a cratered ball. It is a cratered ice ball. You can also, there's games you can play, like, is this Galilean planet or a frying pan? You can see Callisto kind of looks like a frying pan. It's been poorly treated. So, when we talk about Jovian moons, we're going to talk about them by size. The reason we sort the moons by size is basically by the amount of geological activity that's going on, which is a function of the amount of energy that's available. So generally, small moons are going to be frozen rocks. There's not going to be anything going on. Medium-sized moons will have signs of geology. It may not be ongoing. It may be ongoing. We may see evidence of it ongoing, but in general, we're talking about past activity. We don't see active volcanism or active tectonics or active melting of the surface. Large moons, it's going to be ongoing. We'll see a reshaping of the crust every so often. Which way do I run the clicker? Here we go. Medium and large moons tend to be very spherical because they are able to gravitationally pull themselves into a sphere. It is a little bit easier to do that with ice than it is with rock because you're basically breaking weaker structural bonds to force the thing into a circle. And so most of these medium and large moons we see are going to be spherical. Now, the small moons are much more likely to be captured objects, and so they can be potato-shaped. They're generally too small as it is. We figure most of these are formed in orbit around the planets, and they orbit the same way the planet rotates. It's much like, imagine a mini solar system. These groupings of the planets are going to be sort of like the formation of the solar system for each planet. Small moons, potato-like. You see several samples of it, and there are a lot of these. The idea is we find rocks that happen to be orbiting, and maybe it's permanent, maybe it's temporary. Here are some that have been permanent for a while, and they're pretty small rocks. And generally, they're captured asteroids or captured comets, and their orbits are not going to make sense. They'll be all over the place. The large and medium moons generally nice flat plains. Right, so here's the thing: is Jupiter's Galilean moons are basically ice balls, and yet they're very geologically active. There has to be a source of heat, but they're smaller than things like Mercury and the Moon. That, well, on general, Ganymede's larger than, is a fairly large moon, but they're on the scale of objects that have already lost all of their heat. So where is the heat coming from here? And in particular, Io is extremely volcanically active. It's the most active thing in the solar system. But that means it has to have a fair amount of heat to melt material and create lava flows and eruptions. And here we are, seeing some of those ongoing, as we look at the surfaces. And the gist of it is the heating comes from tidal friction. So as a single moon moves around Jupiter, it's going to be on a fairly elliptical orbit. And so it'll feel different stretches over time. So, we imagine our moon orbits in a month, and it's a fairly circular orbit, and not a whole lot of change happens. And the change we see is on the water surface. It's very easy to move. But here, we're moving ice and rock, and it's over a week at the surface is going to flex over and over, or even over just days. The surface is going to flex a lot, and it'll go from very stretched out to not that stretched out and back. And the orbits are elliptical because of the other moons. Is that there's a resonance set up. Every 4 orbits Io makes, Europa makes 2, and Ganymede makes 1. Ganymede makes 1 a week. So 4 times a week, Io goes through this cycle. And this resonance is stationary because every time Io returns to the same point in the orbit, Europa and Ganymede are in a similar position in the orbit. So it gives it a little tug to keep Io's orbit elliptical. And Europa's orbit will also be elliptical. And Ganymede may feel a tug from Callisto. But in general, these things pull on these 3 are the ones that pull on each other and cause lots of tidal friction, which heat the interiors. And so for Europa, what it results in is an icy surface shows signs of melting, of breaking apart and refreezing. Lots of cracks, lots of cracks that show signs of pollution, and in general, it appears as if there's an icy crust floating on a liquid layer, that there is probably a giant ocean of water from underneath. And we'll see signs where cratering can happen and water will well up and form new ice. So we don't see a cratered surface, we see a cracked surface, an icy surface. And we think the interior looks like a metallic core and a thick, rocky interior, and then an ocean layer and an ice layer. Ganymede looks kind of similar. It's more more of a stable surface. There's heavily cratered terrain, but then there's also very young terrain where there's grooves, which are, you might resemble a glacier moving through. And so it looks like ice flows along with cratered. So there's clearly something going on. And Ganymede is a large enough object that both tidal heating and maybe radioactive decay is keeping the body warm enough. Callisto is a cratered ice ball. Because it's the outermost of the Galilean moons, it doesn't benefit from the orbital resonances, so it doesn't get the tidal heating the same way. However, it's a fairly big moon, and it seems to have a magnetic field. So something's going on. There might be some residual magnetism, or it might be an interior that's still liquid and conductive a bit, but it's quite unusual. To be clear, when we tell you that things have magnetic fields, it's because we've measured it. We're not altogether sure why, and our explanation makes sense for big planets, but sometimes we find them and we can't explain why. So, it's a generalization. So, the other large thing in the Jovian moon is Titan. And Titan is particularly interesting, as you can see here, is that it's got a thick atmosphere. One of the thickest atmospheres in the solar system. It's mostly nitrogen, but what's interesting is the liquid that we find in it is hydrocarbons. It's things like methane and ethane and butane and propane, the lesser amounts, but mostly methane and ethane. So it's really intriguing that there's a place where there's a thick enough atmosphere to have weather and to have a warmer interior. It's relatively warmer. It's still going to be fairly cold, but you could have a greenhouse effect here. And so we did some stuff. We probed. We sent the Cassini the Cassini orbiter to Saturn. We also sent the Huygens probe to land. And what we found was essentially a surface that had liquid methane and rocks made out of ice. So I should say stones or pebbles or something like that. We had rock-like features made out of ice. So as we go outwards now, it's mostly medium moons. Saturn has a lot of stuff that is cratered ice balls, but has signs of volcanism and tectonics. Enceladus has shown signs of eruptions. You can see stuff coming off the surface. You can see large features that aren't obviously craters on some of these. Some of these you see massive craters, like Mimas here is the Death Star. Right, but Enceladus is a clear icy surface with ice fountains. We think maybe there's an ocean under it as well. We're not certain of all the details there, but stuff going on in Ice Ball. Iapetus has this weird ridge, which kind of makes you think it's like, if you take hamburger buns and you smush them together, there's a seam. It looks like there's maybe it's something that's smushed together in a sense and formed that ridge. There's lots of varying geological activity. It's not very active, but there's stuff that has went on in the recent past. All right, so we go out to Neptune. Triton is interesting We think it's a precursor. We're going to say that this is a dwarf planet that got captured. It is a Kuiper Belt object. It's got interesting, it's got signs of wind erosion, wind streaking. It's got a cantaloupe terrain, which, ice that is frozen, thawed in different ways. It's similar to Pluto, but it's a fair bit larger. It's got evidence that something has filled in impact basins like lava flows. This lava is going to be water and hydrogen ices that have melted, and so they're molten as they're kind of flowing around. We think this is a captured object. Triton's weird. It orbits retrograde to all the other moons, which means it's going to spiral inwards over time instead of outwards. And generally, stuff that orbits retrograde is almost, we just assume that it's captured in some way. We can't figure out how it would happen otherwise. So, all these icy moons are noticeably more geologically active than rocky objects of the same size. And it's a little surprising because you would expect they don't have heat. And they're even further away. They don't get heat from the sun as much. But the gist of it is that rock melts at high temperatures, so you need lots more heat, lots more energy to cause geological activity. Ice melt at much lower temperature, especially stuff like ammonia and methane can melt at tens of Kelvin. And so tidal heating is significant. It can melt internal ice, and so you don't need an original source for ongoing source. So icy moons can tend to be more active. Didn't mention Saturn's rings. Saturn has rings. Turns out all Jovian systems have rings. Saturn's are spectacular. And you can look up a number of historical theories as to what they are. But the consensus understanding, having probed them, is that there are numerous individual tiny particles that tend to orbit around Saturn's crater, and they're fairly thin. And they're not permanent. All right, we should talk about the structure of them, but we'll eventually talk about where they come from. So when you look in a good telescope, you see a structure. You see a dark line going around with the two bands. What's called the Cassini division. There's two rings. But if we can use a better telescope, much, much, much more individual rings separated by thinner gaps. And it's basically clumps of ice that are moving around, and in general, they form a flat disk. Lots of things in the universe form small flat disks due to conservation of momentum and angular momentum. So we can see in some places where there's gaps, you can see at least in one place in the thick gap that there is an object there, a moon that is moving with it. So some moons, like in the inset, create the gaps. Other moons are going to shepherd the rings. They're going to focus particles into the rings. And so the moons are definitely guiding the rings, and we think they're probably producing the material. You can also see gaps the way you see gaps in the asteroid belt, which we'll talk about in the next chapter. Orbital resonance will cause gaps. It will pull objects toward a moon that's orbiting. So you'll see gaps fill. So the other planets have rings. Here's Jupiter's rings in infrared. They tend to be thin. Neptune has a couple of rings. Uranus has a couple of rings. They're generally smaller and darker particles. They're harder to see. Saturn's happens to be very reflective and very, very big. So it's a noticeable ring pattern. And in general, we figure that the dust is coming from impacts on moons orbiting, because the material is too small. The material should have fallen into the planet or been blown away by solar wind. They can't have survived forever. They have to be continually replaced. And that means it has to come from some source, which is Jovian moons. That's what's available. And in general, random impacts occur, knock material around, and form rings, which then dissipate over time. So Saturn's rings being so beautiful as they are kind of an accident, probably. I believe that's the last of this. So we're going to make a new video here, and next up is going to be small objects of the solar system.